to talk about estimating population means in statistics. So in the last section, we explored distributions of sample means and sample proportions through cases in which we had data for the entire population. This was useful because it allowed us to compare individual sample statistics to actual population parameters. However, it was also somewhat artificial because in most real statistical studies, we have only the sample data, not the complete population data. So let's begin with an example. We all need protein in our diets. And while various organizations and government agencies make slightly different recommendations, the recommended daily allowance for protein is generally around 55 to 60 grams per day for men and 45 to 50 grams per day for women. How does the amount of protein that Americans actually eat compare with these recommended daily allowances? We obviously cannot measure protein intake for the entire population, so we will need to focus on some sample that we hope will be representative of the population. So the figure shows the daily protein intake for a sample of N equal to 267 men. The sample data have a mean of X bar equal to 77.0 grams and a standard deviation of S equal to 58.6 grams. Our goal is to use these sample data to make an inference about the average protein intake for the population of all American men. There are two basic steps to this process, summarized in the following. Suppose that we have computed the sample mean, X bar, for a single sample drawn from a large population. To estimate the population mean, which is mu, we use the sample mean, X bar, as our best estimate of the population mean. We compute a margin of error and use it to construct a confidence interval around our estimate based on the sample size of N and sample standard deviation of S. We can then make a statement that gives us some idea of how good our estimate is. For the example concerning daily protein intake of men, we choose the sample mean of X bar equal to 77.0 grams per day as our best estimate of the population mean. We know that although this is our best and only estimate, it may or may not be a good estimate. So our next step is to calculate the margin of error and construct the confidence interval. A confidence interval is a range of values likely to contain the true value of the population mean. In this text, we will work only with 95% confidence levels, although other levels of confidence, such as 90% or 99%, are sometimes used. The idea of a confidence interval comes directly from the work we did with sampling distributions. Recall that the distribution of sample means is a nearly normal distribution with a mean equal to the population mean of mu. Therefore, the 68, 95, 99.7 rule for normal distributions tells us that approximately 95% of all sample means lie within two standard deviations of the population mean. And the table A1, remember that's the one we use for finding once we have a z-score, we can put it in and find the percent. The table A1 shows that exactly 95% of all sample means lie within 1.96 standard deviations of the mean. The difficulty, of course, is that we don't know the true values of either the population mean or the population standard deviation. Therefore, we can not know the true range in which 95% of all sample means will lie. However, we can use the sample standard deviation and the sample size to calculate a margin of error as defined in the following. So when we use a sample mean as an estimate of the population mean, the margin of error for the 95% confidence interval is E equal to 1.96 S, that's standard deviation, divided by the square root of N, which is our sample number. So similar formulas can be used for other confidence intervals. For example, we can use the table A1 to conclude that for a 90% confidence interval, a confidence level, we will we replace 1.96 in the formula by 1.645, and for a 99% confidence level, we replace it by 2.575. The confidence interval for a population mean always has the sample mean x bar at the center, and extends a distance equal to the margin of error in either direction. So here's our confidence interval. If this is our sample mean of x bar, our margin of error is e. This will be x bar minus e, and on this side will be x bar plus e. We find the confidence interval for a population mean by adding and subtracting the margin of error from the sample mean. That is, the confidence interval ranges from x bar minus the margin of error to x bar plus the margin of error. We can write the confidence interval formally as x bar minus the e is less than mu, which is less than x bar plus e, or in this format of x bar plus or minus e. In this text, we generally use 95% confidence intervals, so e will be equal to 1.96s divided by the square root of n. Consider the daily intake for example 1. We're considering the daily protein intake data described above for a sample of n equal to 267 men, with a sample mean of x bar equal to 77.0 grams and a sample standard deviation of s equal to 58.6 grams. Find the margin of error for a 95% confidence level and construct the 95% confidence interval. How does this interval compare to the recommended daily protein intake for men of 55 to 60 grams? So we use the formula with the given values for the sample to find the margin of error for a 95% confidence level. E is equal to, this is our formula, 1.96 times s divided by the square root of n. So 1.96 times 58.6 divided by the square root of 267. So this is our standard deviation, our s equals, and this is our sample size of n equal to 267. And that'll get us approximately 7.0 grams. We now construct the 95% confidence interval by adding and subtracting the margin of error from the sample mean of x bar equal to 77.0 grams. This gives a 95% confidence interval extending from about 77 minus our 7.0, which gets us 670 grams, to 77 plus 7.0, which is 84 grams. So we can write this result formally as 70 grams less than mu less than 84 grams. This result suggests that American men are consuming a significantly different amount of protein than the recommended daily allowance of 55 to 60 grams. Confidence intervals are easy to construct and are very useful, but we need to be very careful in how we interpret them. The proper interpretation requires thinking about the distribution of sample means. Recall that 95% of all possible samples have a sample mean lying within 1.96 standard deviations of the population mean. Therefore, if we were to repeat the process of obtaining samples and constructing confidence intervals many times, 95% of the confidence intervals would contain the population mean, which is mu, and 5% would not include it. Note, however, that when we have only a single sample, as in the case in most statistical studies, we have no way to know whether it's one of the 95% of all possible samples that actually contains the population mean of mu. It might instead be among the 5% of all possible samples for which the 95% confidence interval does not contain the population mean. So when we choose a single sample and construct its 95% confidence interval, we have no way to know whether that interval actually contains the population mean of mu. However, if we could repeat the process of randomly selecting samples of the same size many times, 95% of the samples will result in confidence intervals that actually contain the population mean of mu. The figure shows a visual interpretation of this idea. The true population mean, mu, is represented by the blue vertical line, running down the middle of the figure. The region to the left of this line represents values below the population mean, and the region to the right represents values above the population mean. So the figure shows the confidence intervals for 20 different samples. In each case, the sample mean, X bar, is the black dot at the center, and the red line shows the 95% confidence interval around the sample mean. So in our chart over here, so here's the true population mean, and the pink line here is our confidence interval, and the black dot is the mean. So we can kind of see that they kind of go this way and that way, and they're kind of, it's around it. But this one's probably the closest one to the line. So these are the values that are going to be below the true mean and the ones above the true mean. So 19 of the 20 samples, which is 95% of them, have a confidence interval that actually contains the population mean. One sample, which is the 6 from the top, this one right here, corresponding to 5% of the samples, has a confidence interval that does not contain the population mean. The subtlety arises from the fact that confidence and probability are not quite the same thing. When we construct a confidence interval around a single sample mean, we have no way to know whether our particular confidence interval is one of the 95% that contain the population mean or one of the 5% that do not. In other words, our confidence interval either does or does not contain the population mean, and any other probability statement would be misleading. All we can say is that 95% of all possible confidence intervals for our sample size would contain the population mean, and 5% would not. Sample 2. The figure shows a histogram for the daily intake of a random sample of n equal to 264 women. The mean of these data is X bar equal to 59.6 grams, and the standard deviation is S equal to 30.5 grams. Estimate the population mean and give a 95% confidence interval. Comment on how these values compare to the recommended daily allowance for women of 45 to 50 grams. So we use our sample mean of X bar equal to 59.6 grams as our best and only estimate of the population mean. To find our 95% confidence interval, we must first find the margin of error using our sample size and the sample standard deviation. So remember, our formula is E equal to 1.96S divided by the square root of n. Our S is 30.5 grams, and our N is the 264. So when we do the calculation, we get 3.7 grams. The 95% confidence interval therefore ranges from about 59.6 minus 3.7, which gets us 59.9 grams, to 59.6 plus 3.7, which equals 63.3 grams. Or 55.9 grams is less than mu, less than 63.3 grams. With 95% confidence, we can say that the mean daily protein intake for women is about 55.9 grams and about 63.3 grams. More formally, if we were to repeat the sampling process many times, 95% of the resulting confidence intervals would contain the true value of the population mean, while 5% would not. We conclude that protein consumption by women is very likely to be different from the recommended daily allowance of 45 to 50 grams. A study conducted by the Garbage Project at the University of Arizona analyzed the contents of garbage discarded by a sample of 62 households. The households ranged in size from 2 to 11 members. The histogram in the figure shows the total weekly garbage production in pounds for the household in the sample. The complete study gives the breakdown of garbage by various categories. The mean for the sample is X bar equal to 27.4 pounds, and the standard deviation is S equal to 12.5 pounds. Estimate the population mean for weekly garbage production with a 95% confidence interval. So we're using our sample mean, as our best and only estimate of the population mean. We use the formula for the margin of error to find that E is equal to 1.96s. Oh, we have some mess up here. It should be divided by the square root of n. So that gets us 1.96 times 12.5 pounds divided by the square root of 62, which equals 3.1 pounds. Sorry for that mess up. So the 95% confidence interval therefore ranges from about 27.4 minus 3.1 and 24.3 pounds to 27.4 plus 3.1 equals to 30.5 pounds. Or 24.3 pounds is less than mu, which is less than 30.5 pounds. All right, with 95% confidence, we can say that the mean amount of garbage discarded by American households is between 24.3 pounds and 30.5 pounds per week. So again, this implies that if we repeated the sampling process many times, 95% of the resulting confidence intervals would contain the true value of the population mean, and 5% would not. So a study by University of Maryland researchers investigated the body temperatures of N equal to 106 subjects. The sample mean of the data set is X bar equal to 98.20 degrees Fahrenheit. And the standard deviation for the sample is S equal to 0.62 degrees Fahrenheit. Estimate the population mean for body temperature with a 95% confidence interval. Well, the sample mean is X bar equal to 98.2, which is our best and only estimate of the population mean for body temperature for a 95% confidence interval. The margin of error will be E is equal to 1.96s divided by the square root of n. Again, it's a little messed up there. Not sure what happened. Which will be equal to 1.96 times our S, which is 0.62. And then we'll divide it by our n. This should be the square root of 106, which is equal to 0.112. So the 95% confidence interval therefore ranges from about 98.2 degrees Fahrenheit minus 0.12 to 98.2 plus 0.12, which we can then state as 98.08 less than mu, less than 98.32. Now notice that our sample mean is 98.2. Our regular thing that we expect to be a normal body temperature is 98.6. So with 95% confidence, we say that the mean, or the average body temperature, is between 98.08 and 98.32. Again, this implies that if we were to select many different samples of size n equals 106 and compute confidence intervals for all of the samples, we expect that 95% of the confidence intervals would contain the true population mean. Notice that the commonly cited mean body temperature for humans is not contained in the confidence interval. Based on this sample, it is likely that the accepted mean body temperatures of 98.6 is wrong. So if you want to find the confidence interval using your calculator, these are the instructions in which you're going to use it on a TI-83 and 84 plus. In planning statistical surveys and experiments, we often know in advance the margin of error we would like to achieve. For example, we might want to estimate the mean cost of a new car to within $200. We can estimate the sample size n needed to ensure this margin of error by solving this formula, which is our formula for error, and solve it for n. With a little bit of algebra, we would find that n is equal to, so basically we're going to multiply the n over, divide by the e, and then to get rid of the square root, we squared both sides. So you don't have to show the algebra, but that's how that comes about. So the exact formula for sample size uses the population standard deviation of sigma in place of S. In practice, we rarely know the population standard deviation because we study only samples. Therefore, to use this formula, we usually estimate the population standard deviation based on previous studies, pilot studies, educated guesses, or we might continue to adjust our estimate of sigma as we collect more sample data. The size of any actual sample must be a whole number, so we round the result of the sample size formula up to the nearest whole number. Any sample larger than this size will give us a margin of error as small as or smaller than the one we seek. So choosing the sample size. In order to estimate the population mean with a specified margin of error of at most E, the size of the sample should be at least, and this is our formula, where sigma is the population standard deviation, often estimated by the sample standard deviation S. So example 5. You want to study housing costs in a rural county by sampling recent house sales. Your goal is to provide a 95% confidence interval estimate of the housing cost. Previous studies suggest that the population standard deviation is about $7,200. What sample size at a minimum should be used to ensure that the sample mean is within $500 of the true population mean and $100 of the true population mean? So for part A, with our E equal to 500 and our sigma estimated as 7,200, the minimum sample size that meets the requirement is, using our formula here, n is equal to 1.96 times sigma divided by E, and square that whole quantity, would be 1.96 times 7,200 divided by 500, and then squaring that, we get 796.6. Because the sample size must be a whole number, we conclude that the sample should include at least 797 prices. So for $100 of the true population mean, our E is equal to 100. Sigma is still the same at 7,200. So our minimum sample size that meets the requirements, plugging those two values into our formula again, we end up with 19,195. So notice that to decrease the margin of error by a factor of 5, we must increase the sample size by a factor of 5 squared, which is 25. This demonstrates that achieving greater accuracy generally comes with a high cost. So pay attention to, if you are decreasing that margin of error, you're going to have a larger and larger sample.